Welcome to the community of
engineers, the change agents in the society.
In this video, we will discuss pure bending in materials made up of several materials. So this is the case of composite materials where structures components made up of more than one materials. We start with the example. Let's say we have a beam and this beam is made of steel and brass. Let's say the Young modulus of steel is 200 gigapascal and Young's modulus of brass, that is 100 gigapascal, and these two materials are bonded together to make one structure of beam. Now the Young's modulus indicates that the brass is not as stiff as the steel is. Now let's calculate it, the ratio of the two moduli denoted with N. So N is equal to Young's modulus of steel upon Young's modulus of brass. So this is 200 gigapascal upon 100 gigapascal. So the ratio of the two moduli is 2. Now here the ratio of the two moduli indicates that the steel is twice strong with regards to the brass, as N is equal to 2. So twice brass would be required to make an equivalent strength of steel. Now let's further discuss using some values. Take as example. Now in this example we have to find first the maximum stress in brass and steel once the beam is subjected to bending moment, which is 6.5 5 kilonewton meter. Further, we have to find the stress between the bond of brass and steel. So, to solve this problem, in fact, there are two ways. One way is there are two ways to solve this problem. One way is to replace the steel with the brass. So twice brass is required to make an equivalent strength of the steel, or the other way, that we replace the brass with the steel. So in this case, half of the steel is required to replace the brass. But the important thing is to note that we cannot change height of the beam or component, because it is important for the centroid, which is used in the flexural formula, that is sigma is equal to mc upon I. However, we can change the width of the component. As we see in this case, we are taking half of the steel to replace the brass. So we are reducing the width, that is 87.5 millimeter, that is half of 175 millimeter of brass. Previously, we were using the brass instead of steel, so we were taking twice brass to replace the steel. So we can see that we were using 350 millimeter width instead of 175. Now, assume we replace steel with the brass. So in this case, the first step to proceed is that we have to calculate the centroid. The overall centroid. So with this y bar, with this equation, summation of individual centroid, the product of individual centroid and the area upon the summation of area. And to do that, we have to make a plot, and this plot, let's say this column is the area, which is in millimeter square. This is the individual centroid, that is of each rectangle, that is in millimeter, and this is the individual centroid, the product of individual centroid and the area, because apparently this cross section is resembles like a two rectangles. So considering rectangle 1, to start with we have to have a reference line. So we draw a reference line here. X-axis is the reference line. All the readings above on the y-axis we are going to take from this reference line of x-axis. Now in this case, the area of rectangle 1, let's say the upper rectangle, that is, this is rectangle 1 and this is rectangle 2. So area of rectangular one, that is going to be 350 multiplied with the height, that is 50, that comes out 17,500 millimeters. And the individual centroid for this rectangular one, that is going to be 225 millimeter, and the product, that is going to be 39,37500 after multiplying this term with the area. Now for the case of second rectangle, the area, that is 175 millimeter multiplied with height, that is 200. So this is going to be 35,000 millimeter square, and the individual centroid, that is 100 millimeter, and the product is going to be 350. Now we have to use sum of areas, that is going to be the sum of these two comes out to be 52,500 millimeter square, and summation of product of individual moduli with the area, that is 7437,500 millimeter cube. Now this term is in millimeter cube. Now using these values in the centroid expression, that is summation of product of individual centroid to area upon summation of area. So this is 7437,500 millimeter cube upon 52,500 millimeter square. So centroid is 141.67 millimeter. So in this figure we can see this is the centroid, overall centroid of the beam. Now using parallel access theorem, we will calculate the inertia about neutral axis, that is I is equal to 1 over 12 BH Q plus area of the rectangle to D square, the distance from the centroid to the individual rectangle. So for that, the first rectangle 1 upon 12 B, that is width 350 millimeters and the height 50 millimeter cube plus area, that is 17500 millimeter square, and the distance, that is 83.33 square, this one, plus for second rectangle, that is 1.12, width is 175 millimeter, height is 200 millimeter cube, plus area, that is 35,000 millimeter square, multiply with the D, that is 41.67 square. Now after solving this, the moment of inertia about neutral axis comes out to 47.908 into 10 raised power 6 millimeter 4, or I is equal to 247.908 into 10 raised power minus 6 meter 4. So after that, now we will solve for brass to calculate the maximum stress of brass, that is MC upon I. Now we know that the brass is at lower side, so M, that is given 6.5 kilonewton meter, and the maximum distance for the maximum stress, that is going to be at the lower end, that is 14167 millimeter upon 247.908 into 10 raised power minus 6 m4. So after solving this, the maximum stress for the brass, that is 3.715 megapascal. Now solving for steel, the maximum stress of steel, that is MC upon moment of inertia. So we know that the steel is on upper half of the beam, so M, that is same 6.5 kilonewton meter, multiply distance from centroid to the upper, and that is 108.33 millimeter upon the centroid, that is 247.908 10 raised power minus 6 m4. So the maximum stress for steel, that comes out to be 2.84 megapascal. Now we have to calculate the stresses between the bonding takes place between brass and the steel, that is this region, where the steel and the brass material that is bonded. So for that, again using the same expression for the case of first brass bond, that is mc upon moment of inertia about neutral axis. So m, that is same 6.5 kilonewton meter. Now for c, we have to calculate this distance up to this. So that is very simple, taking from this to total distance, that is of 108.33 millimeter, and subtracting this by 50 millimeter. So this comes out to be 58.33 millimeter. So this is C is 58.33 millimeter upon moment of inertia, that is 247.908 into 10 raised power minus 6 meter 4. So at bonding, for the case of brass, the value comes out to be 1.529 megapascal. Now to calculate for the stress in steel at bond, we have to simply multiply with the ratio, that is of the two moduli, by this 1.529 megapascal. So this is 2 multiplied with 1.529 megapascal. So stress for the case of steel at bond comes out to be 3.059 megapascal. So with this we end our discussion here.